Okay, in today's lesson we're going to be talking about exponential functions. And so we're going to start off looking at this scenario. We have Raymond Hall, a graphic artist, needs to make several different sized draft copies of an original design. His original graphic design sketch is contained within a rectangle with a width of 4 centimeters, right here, and a length of 6 centimeters, so right here. Using the office copy machine, he magnifies the original 4 centimeter by 6 centimeter design to 120% of the original design size and calls this his first draft. Raymond's second draft results from magnifying the first draft to 120% of its new draft, and each new draft is 120% of the previous. So we are going to have to figure out how to take 4 and 6 and make them 120% bigger. Well, that should be easy. We would take 4 times 120%. Well, that's 1.2. So 4 times 1.2 should give us 4.8. And the same thing with 6. 6 times 1.2 gives me 7.2, and so forth. So let's continue with the things. So if you start with the 4.8 and multiply by 1.2, the next size here, let's just fill in all of our widths. 5.76 times, so if you just hit times 1.2 in your calculator, it'll automatically take that last entry and multiply it by 1.2 again, times 1.2 times 1.2. So we're multiplying by 1.2 each time to increase to be 120% of the last design cell. So what are we actually increasing by, though? Well, 100% would be the exact same. It wouldn't change at all. So our design is actually increasing by 20% each time. That's an 8.64, by the way. Times 1.2, and we get 14.92992. Oops. 2. The resulting draft for each number of 120% magnifications is a unique width and length. Thus, there's a functional relationship between the number of magnifications, n, and the resulting width. There's also a functional relationship between the number of magnifications n and the resulting length. Make a graph using the grid in the My Notes space and the data from the table in item 1. So we're going to start. Let's make a little graph over here. So n, notice in the set pairs, is the horizontal. So notice I'm counting how far up do I need to go? I need to go to like 15, right? So if I make that 15 up there, then the next line would be 14, 13, 12, 11. Here would be 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. So notice on my Y's, I made sure that I was going to get all the width and lengths in there. And on the magnifications, I need to only get to 1, 2, 3, 4, 5. And I'm going to start with this ordered pair, and I'm going to do it in red. When the number of magnifications was 0, we're at 4. When it was at 1, we're at 4.8, so that's a little bit before 5. When we're at the second one, that's a 5.76. Third is at 6.9. That's almost a 7. 4 goes all the way up to 8.2. And 5 is at 9.9, almost 10. For the next one, using a different color or symbol, if you don't have a different color marker, you can actually do like pluses or something like that. How about I do that? So for the length, we're starting off at 6. And at 1, we're at 7.2. So I'm doing little pluses. When we're at the second magnification, we're at 8.64. So there's 8.64 will be there. Third magnification, we're over 10. Fourth magnification, we're at 12.4. And the fifth magnification, we're up to 14.9. So almost at 15. So do these look linear? Well, notice on, especially the width one, it's got kind of a little bit of a curve to it. And actually, so does this one. It's not going in a straight line, or else it would have kept going like that. This one would have kept going like that if it was linear. So I went backwards to get my width values. It's going to be 4, 4.8, 5.76, 6.9, 1, 8.29, and 9.95. Next set of data. And remember, linear functions have a constant rate of change. And rate of change, remember that difference in y's over difference in x's is constant. So let's look at each of these and see if they can be represented by a linear relationship. In other words, is the change in y over the change in x constant? So look at the change in y's. Here, it's going down 3, down 3, down 3, and down 3. So that's the same, but is the change in the x's the same? 2, up 2, up 2, up 2, and up 2. So that change in y's over the change in x's is the same. So that's that rate of change. What else is that called? That's your slope. So I know if I was writing an equation, it'd be y equals mx plus b, right? And what was the b value? Well, that was that y-intercept, right? So, negative 3 over 2, so the change in y over the change in x. What would I have to put as my y-intercept there? Well, you could figure it out, right? Well, let's think about this. The 0 would be right in the middle of that, right? So that would be not a whole negative 3, but negative 1/2 backwards. So if I took 2 and subtracted or added 1.5, that would give me 3.5. That's halfway between 5 and 2. Or I could have wrote 7/2, right? Let's look at the next one. I'll change colors here. We're going up by 3, up by 6, up by 6, and this is up by 9. Now, it doesn't matter if that's the constant. It's the change in y over the change in x being the same. So here, we're going 4 steps. So that's 4 over 3. From 7 to 15 is 8 steps. So 8 over 6 is the same as 4 over 3. That's good. 15 to 23 would be 8 steps. 8 over 6 again, which is equivalent to 4 over 3. Over here we have 12 steps. 12 over 9, again, is equivalent to 4 over 3. So for this one, my slope is 4/3. What would be the y-intercept on this one now? If you have trouble remembering how to find that y-intercept or finding b, remember, you can always plug in an x value and a y value and your slope and find it. Well, how about let's take that point 3, 2. 3 equals 4/3 of x plus b. And let's solve for b. Okay, I'm going to zoom in a little bit so we don't take up as much space. 4/3 times 2 is going to be 8/3 plus b. I need to subtract 8/3 from each side, but it'd be helpful for them to have the same denominator. So what can I do to 3, which is like 3 over 1, to make it have the same denominator so I can subtract that 8/3 from it? Well, if I multiply the numerator and denominator by 3, it would have the same denominator. So 9/3 minus 8/3 is going to equal b. Well, that's 1/3. So plus 1/3. What about this next table? Let's see. So the change in y over the change in x, we're hoping that it's constant. So that's easy on the x's. They're going up by 1 each time, right? What about my y's? Well, this one is going minus 12, minus 6. Uh-oh. It's not. It's not a constant rate of change. So this cannot be represented by a linear function. It does not have a constant rate of change. In other words, we're not adding and subtracting the same thing on our y's each time. The change in y's over the change in x's is not the constant. But what is happening? Maybe it's not adding each time. Could we be multiplying by something? Well, let's look back. We have a 24, 12, 6, 3. It's like we're taking half of each. So how could we represent that? Well, let's go back to the original problem that we looked at. Back in item 1. Copy the width values into the second row of the table here. So here we're trying to find, we want the width values. So if we copy those width values into this table, 4.8, 5.76, 6.91, 8.29, and 9.95. Are we adding the same thing each time? Well, from here to here we're adding 0.8. From here to here it's like 0.9. From here to here it's 1.2. So no, we are not adding the same thing each time. So this is not linear. Whoops. Linear. What we actually have is what is called an exponential function. That is when we're multiplying by the same thing each time. So let's think back on how we change things. So the x values, yes, they were going up by 1 each time. But our exponential growth factor, what were we doing each time? Well, it was 120%, right? So we're multiplying by 1.2. Now let's think about the rate, or the percent increase is a better way to think about that. How much were we increasing by? The growth rate, or percent increase, is actually going up by 20%. So it's a 20% growth rate. We're increasing by 20%. Anytime you're multiplying something larger than 1, you're going to have what's called growth. If it's less than 1, like multiplying by half each time, you're going to go down and down and down and get smaller. We call that decay. So let's think about how we could write the function for that. Well, we started with 4. On the second one, we multiplied by 4 by 1.2. We took that result and multiplied again by 1.2. We took that and multiplied by 1.2 again. So the next row should look, let me zoom in a little bit. Whoops. Should look more like 4 times 1.2 times 1.2 times 1.2, and then we're going to multiply by 1.2 again. That's getting a little annoying, right? Having to do that each time. What's another way we can put that we're multiplying by the same thing over and over and over? Well, could we have put this was 4 times 1.2 squared? 4 times 1.2, 3 times would be cubed. 4 times 1.2 to the 4th. So the next one would be 4 times 1.2 to the 5th. So if I wanted to go all the way to 10, that'd be 4 times 1.2 to the 10th. So the rule would be 4 times 1.2 to the nth power. And let's see if that works even on the 0 and 1. 4 times 1.2 to the first power. This would be 4 times 1.2 to the 0 power.